All right, today we're going to start the second lecture of chapter number 5. And our learning goals for today, the first one, introduce the force of friction. Second, study the nature of different types of friction forces, namely static friction and kinetic friction, and then solve problems that involve forces of friction. So, what is friction and what is causing friction? Uh, if you basically look at the block that we have in this diagram here, and as we discussed that in the preceding lectures, you always, when you look at a diagram, you try to do a free body diagram. That's the weight. That's the normal force. And then there is what we call here pull or push. Okay. Now, this normal force here, it's coming from the contact force between the two surfaces, mean the surface of the block and the supporting surface. Now, the supporting surface will push up with the normal force. But if you try to move the object, you will find a resistance. And that resistance happens because of the contact between the two surfaces. And that usually comes in friction, which we call friction force. So you can basically regard the forces between two surfaces in contact, in this case the block and the supporting surface, as the force that the block pushes up and supporting the surface, which we call the normal, and then the friction force, which here we say component F and component N, and that basically can give you a resultant force which we call contact force. That's another way of looking at it. But usually friction comes as a result of the contact between the two surfaces when you want to slide one over the other. And we say here, when body rests or slides on a surface, the friction force is parallel to the surface. However, as I told you in this textbook, the object will always move around the center of mass. And a block like this is where the center of the mass is. And that's where we put, in some textbook, you may actually find that they try to give the frictional force between the two surfaces. But I told you at the beginning, we always choose the center of mass because this is where objects move. They move around the center of mass, and we look at the effect of that. So that's what friction is. What gives rise to friction? Well, if you take a contact area between two surfaces here and you magnify it, you will see that the surfaces on macroscopic scale are not really smooth, and there is some roughness there. Okay, and this roughness here causes friction. As we say here, friction between two surfaces arises from interaction between molecules on the surfaces. And of course, you know that every material is made from atoms, or if you have compounds, they're basically made of molecules. And if you look carefully with, let's say, good microscopes, you can see these roughnesses. And this basically what causes friction. So when we talk about friction, we're going to talk about two types of friction here. One which we call kinetic friction, the other one which we'll call static friction. And kinetic friction acts when a body slides over a surface. That's what you get. And probably if you're all familiar, if in cold weather, when you take your hands and you basically start rubbing them, you can generate some heat. And that actually comes as a result of friction. And if you look at your hands, you'll find that they're not smooth. They have small grooves on them. And that basically will cause friction, which will generate heat as well. So now, what is the magnitude of this force? Well, here we relate the friction force to the normal force. So the symbol that we have here, N, stands for the normal force. Kinetic friction will use a subscript here, K, to denote the kinetic, so we say Fk. And mu K here is a coefficient of kinetic friction. You know that force is measured in newtons, in units of newtons. The normal force has units of newtons. And the friction force should, of course, have units of a newton. So this coefficient of kinetic friction is unitless, doesn't have any units. But it is the relation between the magnitude of the friction and the normal force. Now, static friction acts when there is no relative motion between bodies. You try to move a block on a surface, but it is not moving, it's resisting the force that you're applying, and where this resistance comes from, basically comes from static friction. And in the same way, static friction is related to the normal force by a coefficient that we call µs, which is equal to the static friction. But we say here that the static friction is less than or greater, less than or equal to µs times the normal force. So here we say that it has a maximum value, because your experience, if you try to push an object which is resting on a surface, the force may be not enough, but if you start increasing your force, then the object breaks loose and start moving. So the friction that is resisting you, it's increasing till it reaches a maximum value. And then at that maximum value, that's it. You don't have any static friction anymore, and the object starts moving. So that's why we say that the maximum static friction that you can have, it will be the µs times the normal force. And that's why here we say that the static friction is less than or equal to µs times the normal force. Let's illustrate that with some examples here. Now what you have here, you have a box and you want to slide this box. So in the first case here, which is case A, if you do your free body diagram, from the center of the mass, you have the weight pointing toward the surface of the earth. You have the normal force, which is basically pushing the block up. And then you're connecting here to a row, which you can basically apply a force. But in this case, the object is not moving, it's at rest, and you are not applying any force. So we say what keeps the object resting here, if we're looking at if we choose this to be x-axis and this is y-axis, then the frictional force in this case is equal to 0. There is no, we cannot say that there is a friction keeping this object from moving, because we are not applying any force. Now, let's take this case here. And now, the weight toward the surface of the Earth, the normal force is up, but you're applying a tension here in the rope. The object is not moving. So there is something that's resisting the movement of this block, and this comes from friction. Now, as I told you, we always try to put the friction between the two surfaces, but I told you always take the effect from the center of the mass. In this case, we say that the static friction here, there is a static friction, which in this case is going to equal the applied force. You apply a tension, but the object is not moving. That means there is a force equal but opposite to it that's preventing you from moving, and in this case it's the friction. But in this case, the frictional force is still less than μs times the normal force. Now, let's take a case when the tension here is just enough to make the block break loose and starts moving. In that case, you're reaching the maximum static friction, which is equal to the μs times the normal force. Now, in that case, the object is going to start moving because the tension that you apply is equal to the static friction. I'm drawing here just to tell you that it should be from the center of the mass, but usually in many textbooks they actually do it between the two surfaces, just to tell you it's originating from there. So as soon as the tension here, which is equaling the friction force, is big enough where the friction force is equal to the maximum value, which is μs times the normal force, the object will break loose and it starts sliding. Now, when it starts sliding, that's it. We don't talk of static friction anymore. We talk about kinetic friction. And this is what we have in this situation here. The weight, center of the Earth, the normal force, the applied tension. But the applied tension now is moving the object. But there is something resisting, which comes from friction. But in this case, it is what? It is the kinetic friction. And the kinetic friction is always equal to the μk times the normal force. So if we try to make a friction force tension graph here, where we apply tension and we measure friction. Now, when there is no applied force, your friction force is equal to 0. When you apply tension and the object is not moving, well, in that case, the static friction equals the tension. And that's why you're getting at any point on this, the tension equals the static friction, which is opposing, and that's why it's not moving till you reach a point where the tension that you apply equals the maximum friction force, which equals μs times the normal force. In that case, the object breaks loose and it starts moving, but in this case, it will be moving with a constant frictional force, which is equal to the μk times the normal force. So when there is no movement, you apply a force, there is no movement, while what's opposing you is basically static friction. When you move, well, the friction has an effect in slowing you down, and in this case, it is what? It is kinetic friction. Are these clear now? Now, we related the static friction as less or equal to the mu s times the normal force, the kinetic friction mu k times the normal force. And I told you that the units of the normal force is in newtons, and you measure your forces in newtons. So the coefficient here, mu s or mu k, are unitless. They don't have any units. And we call them coefficient. In the case of S, we call it coefficient of static friction. In the case of kinetic, we call it coefficient of kinetic friction. And that's what we have here. Coefficient of static friction, mu S, coefficient of kinetic friction, mu K. The coefficient of kinetic friction is less than the coefficient of static friction. So if you take a block made of steel and you move it on a table that's made of, the surface of it is made of steel. If you measure the coefficient of static friction, it's equal to 0.74, but the coefficient of kinetic friction is 0.75, which is less. The table here gives you the different coefficient of static and kinetic friction between different materials. For example, aluminum on steel, copper on steel, brass on steel, zinc on cast iron, and you move down like this. And these are basically the coefficient of static friction, and these are the coefficient of kinetic friction, but always kinetic friction, the coefficient of kinetic friction is less than the coefficient of static friction. Now, if you're given an assignment where you have to solve problems and you have time to do that, sometimes they may not give you the coefficient of either coefficient of static friction or kinetic friction, but if they tell you the type of the material, then you can basically come and look in this table or different tables where you can extract the coefficient of static friction or kinetic friction. But if I give you, let's say, a problem, an exam or a quiz, and I don't give you a table where I will give you the value of the coefficient of static friction or the value of coefficient of kinetic friction, unless I ask you to find that. So this, if you're dealing with an assignment and you're not given these coefficients, look what the material of the surface and the block and the surface are made of, and you can basically dig this information out. Now, one point that I want to clarify before I move on into solving problems, and which I dealt with in the last lecture, is when you have an incline. I think I got some questions on that as well. And I told you, when you try to do your free body diagram and you want to take components, what angle does the weight makes with the y-axis, which should be normal to the incline. So for example, if you have a block resting on an incline like this, well, this is the weight which points toward the surface of the earth, the normal force which basically acting up. The second thing is to choose x and y, and I told you always take an x which should be along the motion, and in this case it will be along the incline. The y-axis will be perpendicular to it. As soon as you do that, you will find that your weight makes an angle with your y-axis. And I told you in the last lecture that the angle of the incline, it is the same angle between the y-axis and the weight. So we'll go through it again here. Now you know that if you take this triangle here, the total angles here should be 180 degrees. So you say 180 degrees. This should be equal alpha plus 90 here plus, let's call this angle theta. So now if you look at the angle between the incline, that means the x-axis, and the y-axis, it's 90 degrees. But this angle, it's the angle theta that the incline makes with the x-axis, plus the angle alpha, or we don't know what the angle that it's make with the y-axis here. So from this one here, I can take this to the other side. So I'll have 180 degrees minus 90, and that of course will give me 90 degrees, and that should equal to alpha plus theta. So if this angle here is theta, but this should be 90 degrees, means theta plus alpha is equal to 90 degrees. Well, that means this angle here, I could have called it beta, but it's equal to what? It's equal to alpha, and that's the reason why, as I told you in the last lecture, when you choose your y-axis to be perpendicular to the incline, your weight will make an angle with this y-axis, and the angle between the weight and the incline will be the same angle of the incline relative to the horizontal surface. Now, when you have the weight, you have to take components of this weight. So when you look at this, this is acting this way. So it will make an x component this way, because this is our x-axis, and it will make a y component which is basically pointing along the y-axis. If you notice, the angle here is alpha, so if you take cosine alpha, it will be the adjacent, which will be wy, and of course the hypotenuse will be y. And that tells you that the y component will be the weight cosine alpha. And if you look at the sine alpha, you will find it is wx over w, which will tell you that the x component of the weight will be the weight sine alpha. Now, you're familiar from chapter number 1, when you take a vector and you take the components of the vector, if you consider the angle that the vector make with the positive x-axis, then your x component is with cosine and your y component is with a sine. But in this case here, we're looking at the angle that the vector, in this case, it's the weight that makes with the negative y-axis. Okay. And that's why we have the y component of the weight here is w cosine alpha, and wx here is equal to w sine alpha. I just wanted to clarify this point before I move on. Okay, is this clear? So let's deal with some examples here. And the first example that we have here, you want to move a 500 Newton crate. So right away, they give you the weight here. You know, when the units are given in newtons, you're given the weight. Cross a level floor. To start the crate moving, you have to pull with 230 Newton horizontal force. They tell you to start moving. So you know, when there is an object resting on a surface and you want to move, you have to apply a force, but you know that there would be friction opposing you. And the maximum friction, the maximum static friction happens when we said it's mu(s) times the normal force, and that's when you brake. That's why you need 230 newtons to start moving the object. Once the crate breaks loose and start to move, you can keep it moving with constant velocity with 200 Newton. And that will basically make it moving with constant velocity, but now the pressure that, tension that you apply is less. And they ask you here to find the coefficient of static and kinetic friction. So in both cases here, if you go to the center of the mass and you try to draw your free body diagram, the weight is down, the normal force is up, the tension is this way, friction will be opposing you the other way. But you have two situations here. One situation is for the static, and the other situation when you have what? When you have kinetic. So you draw your x-axis, you take your x-axis along the motion. So in this case here, this will be the x-axis, this will be the y-axis. That's the weight, which is 500 newtons. That's the normal force. The tension that you apply here is 230 Newton, and it should equal to the maximum static friction because you want to break this object loose. So if you want to analyze that, you will say that along the x-axis, you have the tension, which is acting positive, minus the Fs max, and that should equal to 0 in this case. They're just equaling each other. So out of this one here, the Fs max will equal to the tension. And the tension here equals 230 newtons. And your maximum static friction should equal to the mu Sn. So you need the normal force. So if you go to your y, summation in the y should equal to the normal up minus the weight down, and that's equal to 0 because there is no motion along the y. And this basically gives you that the normal force is equal to the weight. And that's why you say here that the weight equals to the normal force. So now, if I want to get my mu s, it should equal to the tension divided by the normal force. The tension here is 230 newtons. The weight is 500 newtons. And of course, it will give me 0.46. And I told you that the mu s is unitless. There are no units for this. Is this clear so far? So that's the mu s. Now, in the case when I want to look at calculating the coefficient of static friction, but they gave me a condition where you're going to be moving with constant velocity, and constant velocity means A equal to 0. So again, you have the weight, you have the normal force, the tension, in this case it's 200 newtons, and opposite to that is the kinetic friction force. You will do the same thing. Summation of Fx will be T minus Fk should equal to Ma, but your A here is equal to 0 because you're moving with constant velocity, meaning that your tension equals to the Fk. And you know that the Fk should equal to the mu k times the normal force. Where can we get the normal force? Well, you look at the y. Summation along the y should equal to normal up minus weight down. It's not moving along the y, which is equal to 0. And that basically gives you that the normal force is equal to the weight. So the friction force here is equal, the kinetic friction is equal to the mu k times the normal force. So the mu k here should equal to the friction force divided by the normal force. The normal force is equal to the weight, which is 500 newtons. And your friction force here should equal to the tension, which should equal to 200 newtons. Okay. So it's 200 divided by 500, and it gives you 0.4. And that's how we obtain the coefficients of static and kinetic friction in this case. Is this clear? Any question on this? Let's take another example here. You move a 500 crate by pulling at an angle of 30 degrees above the horizontal. How hard must you pull to keep it moving with constant velocity? Assume that the coefficient of kinetic friction is equal to 0.4. They're giving you the weight, and you're pulling at an angle of 30 degrees, but they're asking you, the object is moving horizontally. How hard should you pull? So if we do that, we're going to do a free body diagram. And as I told you, always go to the center of the mass. Weight is down. Normal force is up. Tension is this way. And in this case, you only have friction, and the friction basically operating in the opposite direction. You will choose an X and Y, always X along the direction of the motion. Y will be normal to it. Tension, which we have here, will make an angle with the positive x-axis of 30 degrees. So you have here an X component of the tension, which is T cosine 30. And here you will have a Y component of the tension, which is T sine 30. And they're asking you, how hard are you going to pull? Now, on the side here, instead of putting T, we just put F here to tell you that it is a force, because they did not ask about the tension. Just to be clear, they ask about how hard. That means your force that you apply. And the force that you apply, it's coming at an angle of 30 degrees. So again, it will have an X component, which is F cosine 30 degrees, and a Y component, which is equal to F sine 30 degrees. They tell you that it's constant velocity, meaning that A is equal to 0. So the summation of the force along the x-axis will equal to 0. And the forces that you have along the x-axis, you have the x component of the applied force, and that's why you say F subscript x here, minus the friction should equal to 0. So F cosine 30, which is your X component of the applied force, should equal to the Fk, because you can take this to the other side. And the Fk is equal to the mu k times the normal force. So you need to know the normal force. From the Y, the Fy is equal to 0. Now, when you go to the Y, you have the normal force acting up, and this force will have a Y component, which also acting up, minus the weight equals 0. So if I want to get the normal force, I will take the Fy and the W to the other side. So the normal force here will equal to the weight minus the Y component of the force, which will be the weight F sine 30 degrees here. So the normal force here, it's equal to the weight F sine 30 degrees. And I think I reminded you when we talked about Newton's third law, I told you that weight and normal force are not action-reaction forces. I warned you about that. And I think in the last lecture, I also warned you that many people think that the normal force should equal to the weight, which is equal to mg. And this is a case here. Actually, it's resting on a horizontal surface, but the normal force is not just equal to the weight, because there is a component of the force which is pulling up as well. It's helping the surface. And that's why the normal force here is going to be less. So you have to be careful with that. Now, we talked about we said that the F cosine 30 is equal to the mu k times the normal force. So F cosine 30 equal mu k times the normal force. In this case, it's the weight minus F sine 30. Now we can rearrange this equation by multiplying the mu k and taking this to the other side, and you can take it as a common factor. So you will have F multiplied by cosine 30 plus mu k sine 30 equals mu k times the weight. So the F now will equal to the mu k times the weight divided by cosine 30 plus mu k sine 30 degrees. The mu k is 0.4, weight is 500, cosine 30 plus 0.4 sine 30, and this gives you 187.6 newtons. So the force that you have to apply to keep the block moving with constant velocity horizontally, in this case, it will be 187.6 newtons. Is this clear? Any question on this one? Now, we dealt with this in the last lecture when we looked at the acceleration of the toboggan on incline that makes angle alpha with the horizontal surface. And here we'll do it, but we include the friction as well. So if you recall, and I'll just write it down, in the last lecture, we said A should equal to G sine alpha. That's when we did not consider friction. No friction, okay? That was the case. Now, in this case here, when you do your free body diagram, the weight, which will be acting down toward the center of the earth, normal force, which is basically norming to the supporting surface, and then you have the friction, which is opposing your motion. Again, I don't have to explain this. The weight makes an angle alpha with the y-axis of our choice. So here, the y-axis is W cosine alpha. And the x component of the weight is W sine alpha. So if you look along the y, you will have here, if you look at the y-axis, you will have the normal force minus the y component of the weight is equal to 0, meaning that the normal force is equal to the y component of the weight. And that's why we say here the normal force equals to the y component of the weight, which should equal to W cosine alpha. We need the normal force in order to calculate the friction force. Along the x, the summation of Fx should equal to MAX. What you have along the x-axis, if you choose down being the positive, which is the motion in this case, it will be the Wx, the x component of the weight, minus the kinetic force of kinetic friction should equal to MA. Mg sine alpha is the x component of your weight. Mu k, the n is equal to the y component of your weight, which will be mu k W cosine alpha should equal to MAX. You substitute for W mg, so you have mg sine alpha minus mu k mg cosine alpha equals MA. You can cancel the M out. So your acceleration here now is equal to G sine alpha minus mu k G cosine alpha. So your acceleration now when there is a friction is less by this factor here. That's what we did in the last lecture when we did not consider friction. Now, if you consider friction, you will find your acceleration is less. Is this clear? Any question on this one? Let's take a problem here, and we'll do it for a system. And we'll just take a system of 2 blocks. So in the following figure, you have mass 1 here, which is 20 kg. Alpha is 53 degrees. The coefficient of kinetic friction between the block and the incline, mu k equal to 0.4. What must be the mass M2 of the hanging block if it is to descend 9.5 in the first 3 seconds after the system is released from rest? So you can always start with your free body diagram, and you can always come to the center of mass. You will have the weight, let's call it W2 here. And then you have a cable which is pulling, let's call it T. That's for M1. Let's go for M2. You come to the center of the mass, okay. Now, when you do that for the M1, weight will be basically pulling down, let's call this W1. The normal force, let's call it N1, since we don't have a normal force on the other side, but with this, okay. And then you have a T here and tension. Now, I should bring it to your attention here that we always say a light cord, a light cable, a light rope. So we are neglecting the mass of the cable to make it simple in these type of problems. But since this is descending down, this rope here, if it has good mass, it will add to the mass as it comes down. And of course, we may have to do some sort of integration, but to simplify, we always ignore that. So that's one thing we always do in these types of problem. We did not write it in this problem, but we say a light cable, ignore the mass of the cable, rope, whatever it is. The second assumption that we always make is the pulleys here are frictionless pulleys, meaning that the rope can slide over them. And if the rope can slide over them, that means the tension here and the tension here is the same. But if it's rotating, and we'll see that when we deal with rotational motion, that will make a factor. So in these type of problems, we make some assumptions. First, the pulleys are frictionless, meaning that the cable or the rope or whatever is sliding over them. The second, we ignore the mass of the rope, and that could complicate things. And we also ignore air resistance as well. You can basically go through liquids. It could be complicated more this, but to simplify things, we're ignoring all of these things here. Okay, to make it simpler, just to illustrate the point of what we're trying to do. Now, as I told you in the last lecture, you can always choose different axes for these. So for this one here, you can choose your X and Y. Now, the object is descending down, so you can choose your Y down, but I did it here on purpose just to tell you that you can always, things will work out. So I made the Y-axis up in this situation here. So when I look at my forces in the X-axis, I don't have forces in the X-axis. I'm only doing that for M2, so it's equal to 0. For the Y, I have T acting up, minus mg acting down, and I put a minus sign here because the acceleration is downward, which is equal to minus m2a. If you want to choose to put it Down this way, you will say that it is M2G minus T is equal to M2A, which is same way, okay, if you want to do it that way. So out of this equation here, I can take this to the other side. So the tension here will equal to M2 times G minus A. Now, in terms for the A here, I want to find out the value of the tension. Okay. And actually, they asked me the value for M1. What should be the mass for M1? But they gave me a condition that it will be descending 9.5 meters in 3 seconds. And that's where I'm going to use the knowledge that we did in kinematics. You know that since it's going down along the y, you know that when we said y equal to y0 plus v0 yt minus plus 1/2 ay t squared. That's not free fall. If it's free fall, you have no cable, but you have a cable here, so it's not free fall. If you take this to the other side there, then you have delta y will equal to the vy0 t plus 1/2 ay t squared. So what we have here, we say that delta y equal to the v, and we put 2 here to indicate that it is mass 2 plus 1/2 at squared. Delta y is 2.5. Is starting from rest. So this will equal to 0. Plus 1/2 ay t squared. So if you want to get the ay, you can multiply this by 2. It will cancel the half. So you have 2 times 9.5. You have to divide by 3 squared, which is 9. That's why you said the ay is equal to 2 times 9.5 divided by 9. And that will give you 2.1 meters per second. So we say that the magnitude of this acceleration here, it's equal to 2.1 meters per second squared, meaning that the mass 2 will be descending down with an acceleration of 2.1 meters per second squared in magnitude, and mass 1 will be going up the incline with acceleration equal to 2.1 meters per second squared. Since we dealt with M2, we can go and do that for M1. For M1, along the x-axis, you have the tension, which is pulling along the positive x-axis, because this will be your x and this will be your y. You have the friction, which is opposite to your motion, which is equal to Fk minus m1g sine alpha. The weight here, if you choose your y-axis, so the weight is acting along the negative x-axis here. So it's m1g sine alpha equals m1a, because the system is moving along the positive x-axis direction here. Now, Fk is equal to mu k times the normal force. So you need the normal force. So if we look at y, along the y, we have the normal force, and we call it N1 here, equal to m1g cosine alpha, which is the y component of the weight, equals 0. So the normal weight here is equal to m1g cosine alpha, which makes the Fk is equal to mu k times m1g cosine alpha. Now you can put the Fk here. So you'll have T minus mu k m1g minus m1g sine alpha equals m1a. And this is what we have here. T minus mu k m1g cosine alpha minus m1g sine alpha equals ma. T here, if you go back to the slide before, and we figured out that the T should equal to m2 times g minus a. So we substitute here for the T m2 times G minus A minus mu K M1G cosine alpha minus M1G sine alpha. I'm interested in M2. So you can take these to the other side. So you'll have M1A plus mu K M1G cosine alpha plus M1G sine alpha will equal to M2 times G minus A. If you divide by G minus A, it will give you the M2. You plug in your numbers. M1 is 20. The acceleration is 2.1. Mu K is 0.4. 29.8 cosine 53 plus 20 times 9.8 sine 53 over 9.8 minus 2.1. And this gives you 31.91 kg. So that's what M2 should be for the system that we have here to descend 2.5 meters from rest in 3 seconds. Is this clear? Is this clear? Any question on this one? So that's the idea here when you're dealing. By the way, we can complicate this. We can include more object in this problem, but I told you we simplify things here by not the cables are light. We ignore their masses. The pulleys are frictionless, so the ropes or the cable can slide over them. Of course, if you continue with physics and you take other courses, all of these things are going to be considered. Okay. So what we did, we only introduced two things today. We introduced the static friction and the kinetic friction. And we said that the force of static friction is less than or equal to the mu s times the normal force. The kinetic force of kinetic friction is mu k times the normal force. And we added these in our treatment when we look application of Newton's either first law or second law. So we just added these two forces. Let's take two questions here to discuss. The first one, motion on a slope having friction, but we say that A is equal to 0. That means you're moving with constant velocity. So consider a toboggan that is sliding down incline with constant speed. Find the mu K. We already have done this, okay? When we dealt with the toboggan and we said that the acceleration is equal to G sine alpha minus mu K times G cosine alpha. So all we have to do is look at this result here. We don't have to work it out again. But the condition is at constant speed, that means acceleration is equal to 0, meaning that 0 equal to G sine alpha minus mu K G cosine alpha. And that, of course, will tell you that G sine alpha should equal to mu K G cosine alpha. So you can take the mu K by dividing this here. And that's why you have the mu K equal to G sine alpha over G cosine alpha. The G cancels out. And sine alpha over cosine alpha will give you tan alpha. So the mu K in this case is equal to tan alpha if the object is sliding down with constant speed. Again, if there is no friction, A here will equal to G sine alpha, and it cannot slide down with constant speed. Only if there is a friction. If there is a friction, of course, we'll be working in the opposite direction, and that can slow things down, and you may actually achieve constant speed as you go down. Is this clear? Any question on these? Now, in this problem here, what is the friction force of the crate is at rest on a surface, and a horizontal force of 50 Newton is applied on it. Again, you always free body diagram, weight is down, normal forces up. That's the applied force here. And of course, this will be the, in this case, static friction working in the opposite direction. It is basically on rest. It's at rest, so it's not moving. So if you look at your summation of the forces along the x-axis, it will be the applied force minus the force of static friction should equal to 0, meaning that the static friction should equal to the applied force, and that's why we said it's 50 newtons here. And of course, it's not the maximum static friction yet, that's why it's still at rest. When you achieve the maximum static friction, then it can break loose and start basically moving. So all what we did today, we just introduced the friction force today. And we related the friction to the normal force. And I told you that you have to be careful. The normal force is not just equal to the weight. You have to calculate that. Any questions so far? Any questions? So for today, we basically talked about the static friction, and we said it's less than or equal to the mu(s) times the normal force, and maximum static friction happens at mu(s) times the normal force. An object will break loose. As soon as they break loose and they start moving, you no longer have a static friction, you have kinetic friction, and the kinetic friction is equal to the mu k times the normal force. And all what you have to do is, in your problems now, include in the friction, and then you can calculate acceleration of the system. And once you know the acceleration, you can apply it to your kinematics, and you know how fast the system will move and how long it will take it to descend or move or whatever you want to do. But there are some cautions that I'll tell you here. When you're dealing with weight and normal force, they are not action-reaction forces. The normal force is not equal to the weight. It's not equal to mg. Okay. Sometimes it just takes a component of the weight when it's in an incline. And if there are forces that are making components along the positive y-axis, you will find that the normal force also affected by that. Any questions on these? Any questions? Clear? Good.